Alright, for this problem here related to simple harmonic motion, we have a pendulum. It's created by attaching a heavy mass to a rod and connecting it to a frictionless hinge, something like this. And that pendulum is going to swing back and forth. And initially the period of oscillation is t. We want to know the new period of oscillation when the following things happen to this pendulum. So for this first one, we want to know what the new period of oscillation is when the amplitude is doubled. So I'm going to think about this. I'm going to think about the period for a pendulum and the fact that it's 2 pi times the square root of L over G. And that's going to help me determine all of these quantities here. So for this first one, what happens when the amplitude is doubled? We see the amplitude is not present at all in this equation. So that means that we have the same period. Our period is still going to be equal to t in this situation. For the second one, what's going to happen when the mass on the pendulum is tripled? Once again, we look at this equation, and for a pendulum, neither mass nor amplitude matters. The only things that affect it are L, the length of the pendulum, and G, gravity. And so, once again, we're going to have the same period even if we double our mass here. It's still going to be a period of t. For the last one, we actually do have a change here. What happens when the length is reduced by a factor of 4/9? So I'm going to set up an equation here. T equals 2 pi times the square root of 4/9 L all over G. I'm going to pull out that 4/9 term and put it out in front here. So I'm going to have T equals the square root of 4/9. It's got to stay under that root, times 2 pi times the square root of L over G. I can go ahead and mathematically take the square root of 4/9. Square root of 4/9 is just 2/3. So it's 2/3 times 2 pi times the square root of L over G. And this term here ends up being my original period. Okay, I really should call this one here T prime because it's my new period. And so I find that T prime, that new period when the length is only 4/9 as much, is going to be equal to 2/3 times T, which is my original period. Alright, so this first one here, we have a person designing an experiment to prove the relationship or the equation for a mass oscillating on a spring given by this equation here that we've been using. They're going to go ahead and collect data regarding the period for an oscillating object and vary a bunch of things and ultimately create some graphs. We want to know what these graphs would look like. So for the first one, we want to describe the graph of period versus amplitude. And what we would see for that period versus amplitude graph is we would just see no relationship here. Okay, we know that the amplitude has no effect whatsoever on the period, so changing the amplitude won't change the period at all, and we'll just have a horizontal line. We don't need to linearize this at all. For this next one, we want to know what the graph of period versus mass would look like. So we'll have period on our y-axis, mass on our x-axis. This one would not be a horizontal line. The mass absolutely does affect it. And we can say period is proportional to the square root of 1 over the mass. And so this graph would look like a square root graph, something like that. And what we would need to do here to linearize this is we'd need to go ahead and graph period versus the square root of the mass, and that would give us a linear graph. For this last one here, we're going to have period versus our spring constant, and that one's a little bit tricky. So let's think about that relationship first and then think about what the graph would look like. The period is going to be proportional to the square root of 1 over the spring constant. So it's going to be both linear, or it's going to be both a square root graph and an inverse graph. So it's going to look something like that. Okay. And so in order to linearize it, we would end up graphing the period versus 1 over the square root of the spring constant. Okay, and that would ultimately give us a linear graph. Alright, for this problem, we have a box that's sliding along a frictionless surface at a speed of v. It has a mass of 2m, and it collides with another box with a mass of m that's initially at rest and attached to a spring. We first want to derive an expression for the velocity of the two boxes after the collision. In order to analyze a collision here, we're going to think about conservation of momentum. So momentum initial equals momentum final. So initially, it's just going to be the mass and velocity of box 1, and then the two boxes are going to stick together. So we're going to have their combined masses times their final velocity. So we have 2m times v is going to be equal to 2m plus m times v final. The masses can cancel out there, and what we're ultimately left with is 2v equals 3v final. So that means our final velocity is just going to be 2/3 of that initial velocity there, v. All right, next we want to derive an expression of the period of oscillation of our system. So that's going to be 2 pi times the square root of the mass over k, our spring constant. K is just k, that's what it's given as in our problem here. And our mass is going to be 3m, so it's just going to be 2 pi times the square root of 3m over k. For part C here, we want to figure out the amplitude of oscillation of the system, and so to do that, I'm actually going to think about conservation of energy here. I know that once my system begins oscillating, I start with all kinetic energy, and that kinetic energy gets transferred into spring potential energy, and I can solve for x, the distance the spring is stretched or compressed, and when it's at its maximum compression, okay, when it's all spring potential energy, that will be my amplitude, that distance stretched or compressed. So I can say 1/2 mv squared, my kinetic energy equals 1/2 kx squared. My spring potential energy, the 1/2 will cancel out. I know two things from above because we do want to answer in terms of these same variables here. I know my mass is just going to be 3m. I know my velocity is 2/3 v, that quantity squared, and that's going to be equal to k times x squared, ultimately solving for x here. So this left side is going to be 3m times 4/9 v squared, all right, equals kx squared. The 3 and the 9 will cancel out to make that a 3. And then I'm going to divide both sides by k and take the square root here, and what I end up getting is that 4mv squared over 3k, the square root of that, is equal to x, my distance stretched or compressed. All right, for question D, we want to know what will happen to the following quantities if we flip the position of these two masses. So if we have mass m initially moving at a speed of v colliding with mass 2m attached to the spring initially at rest. So how would that affect the period, the frequency, and the amplitude? So for this, the period and frequency are going to ultimately stay the same. If we think about our equation for period, it's just 2 pi times the square root of m over k. Because the total mass that's oscillating hasn't changed, that position's irrelevant. The total mass is still 3m. Our spring constant is still the same. Our period will still be the same, and therefore so will our frequency. So both of those remain unchanged. Our amplitude, however, will change. If we think about what we did before, we were looking at energy here. Before, we were looking at our kinetic energy becoming spring potential. When we flip those two, all right, the velocity of them is going to actually be smaller, okay? And that actually goes back to momentum. We're going to have a smaller velocity after the collision because there was less momentum in our system initially, and that means we're going to have a smaller kinetic energy when we start oscillating, and therefore a smaller spring potential energy, so our amplitude will decrease. All right, now we're going to make graphs showing this motion, and so we're going to start with the position versus time graph. We first want to label the amplitude, so I'm going to say it goes from the square root of 4mv squared over 3k, that's my amplitude, down to negative square root of 4mv squared over 3k. And I'm going to say that one period is that distance, two of the thicker bars there. All right, we're going to draw at least 2 full periods. So this box is going to start at its equilibrium position. Okay, we know once that collision happens, that's when they begin oscillating. It's going to go up to its amplitude, back to equilibrium, down to its negative amplitude, and then back to 0. And so that's what one full period would look like. And then there is 2 full periods, all right? It's going to be a sine curve, and we're just doing a basic sketch. so you don't have to worry too much about the actual curvature, but you should show 2 full periods, and you should show it going to its amplitude there. For the velocity versus time graph, we once again can label our maximum points. I'm just going to say they're at the same locations. Obviously the scale is different because one's meters per second, but the maximum velocity is going to be 2/3 v, and the minimum, or the maximum negative, I really should say, is negative 2/3 v. So it does matter where we start here. Okay, our periods will be the same, but it does matter where we start. Initially, we have a positive velocity, and we're at a maximum, and we can see that from the position versus time graph. We have a positive slope here, and it's the greatest possible slope. We also can think about the fact that we start out moving at our maximum speed. So we're going to start out up there. Okay, we're going to drop down to 0. All right, that's this point right here. Then we're going to be at a maximum negative velocity, which is this point here. Then we're going to be back to 0, which represents this point right here, and then back to our maximum positive velocity for 1 full period. And on a position graph, that's back to where we started. All right, so this graph is going to look something like this, and I'm just going to sketch that next period. All right, and so that's what our velocity versus time graph would look like. Finally, we have our acceleration versus time graph. We don't actually know our maximum or minimum acceleration, so we don't really have to worry about that. But we're still going to sketch our graph. Same thing, I'm going to mark off where a full period is. And I'm going to use my velocity versus time graph to figure out my acceleration. So I'm starting here at this point. The slope of that line when I'm at these peaks here is going to be 0. So that means my acceleration versus time graph starts at 0. All right. And then this next point here is a negative acceleration. So we're actually going down first. Okay. Then we are back to 0 at this point here. So back to 0 on my graph. Then we have a positive acceleration. That's this point here. And that's going to be that maximum positive acceleration. And then lastly, we are back to 0 to round out that first full period. And so it ends up looking like this. The acceleration versus time graph always ends up being the flip of the position versus time graph. And if you are in calculus, you know that because when you take the derivative of sine twice, you get negative sine. All right, and so this is a sine curve here starting at 0. This is negative sine. All right, for this problem here, we have a wave pool, and the surfers are upset that the waves are not moving fast enough, and we want to know what we could do to change those waves, and the key to this is to change the medium. So there's lots of possible options. We could change the depth of the water, we could change the temperature of the water, but you have to change something about the medium, which in this case is the water that the waves are traveling through. All right, for this one we have a bunch of different wave phenomenon, and we want to state which of the shun words, which of the wave properties each one describes. All right, so we'll go through these one at a time. So for this first one, sound waves hit a mountain and bounce back, creating a good echo for yodelers. That is going to be reflection, bouncing off of a surface. For B, when a water wave hits a sandbar and the depth of the water decreases, the wave changes directions. That's a case of refraction. All right, we're changing the medium, in this case the depth of the water, and that changes the direction of the wave, causes it to bend. For C, water waves spread out when traveling through a narrow opening to a bay. That's going to be diffraction, the fact that waves spread out when going through an opening. D, when two water waves collide, it makes an even bigger wave. That's an example of superposition, the two waves combining to make a bigger wave. E, sound waves travel better over water because the cold air bends the sound waves back down towards the surface. That's another example of refraction, okay? Changing the medium, in this case the temperature of the air, causes the waves to bend. For F, a soprano and a baritone sing at the same time. It produces a more complex wave. That's an example of superposition, the two waves combining to form a bigger, smaller, more complex wave. And lastly, it's difficult to hear in a gymnasium because the sound bounces off the walls. That's another example of reflection. For 6 here, we have 3 graphs, and we want to think about ranking the 3 of them based off of various things here. So the first thing we're going to rank is lowest to highest pitch. So pitch, we're really thinking about frequency here. Okay, that's what the pitch depends on. And when we're thinking about frequency, we don't actually see frequency on this graph, but we do see the period, okay? from here to here, the time for one full wavelength. And so we can think about the fact that frequency is just 1 divided by that period. All right. So if we want the lowest pitch, okay, that's going to be the biggest period, the longest period. And so that's going to be wave C here, has the longest period, 0.002 seconds. So C is going to be the lowest pitch. It's going to have a lower frequency than B, which has the second smallest period. And that's going to have a lower frequency than A, which has the smallest period, and therefore the highest frequency and highest pitch. For B, we're going to rank shortest to longest wavelength. Again, we don't actually see wavelength on here, but what I would think about is the fact that velocity equals wavelength times frequency. Okay, that velocity is going to be constant because the medium is not changing for these 3 waves, and so as the frequency gets smaller, the wavelength gets bigger. So if we're going from shortest to longest wavelength, A with the biggest frequency, highest pitch, actually has the shortest wavelength. B is in the middle, and then C with the lowest frequency, lowest pitch, has the biggest or longest wavelength. For C, we're going to rank them from quietest to loudest, and for that we're thinking about the amplitude here. So we're thinking about this peak here. So this one's at, looks like 0.5 pascals. This one's measured in pressure because it's a sound wave, and that's one possible unit for amplitude. And then B and C are both at 1 pascal. So quietest one is going to be A, and that's going to be less than B, which is equal to C. They have the same amplitude, so they have the same volume. And lastly, rank the velocity of the waves. We know that they're all traveling through the same medium, and therefore, regardless of amplitude, frequency, wavelength, etc., they all have the same speed.